Welcome, everyone. For today's prep, we're going to be looking at limits at infinity. So this is really a new type of limit that we're going to be considering. So let's put it in the context of all the other limits that we've done so far. So every single limit that we've done up to this point has been when x is approaching a specific number. So we've done overall limits, we've done right-hand limits where x is approaching a number from the right, we've done left-hand limits, things like this. So normally the way this procedure works is we find a specific x value and we investigate what happens if we use inputs that are getting closer from the left, and we see the corresponding change in our function. And we've also done right-hand limits. So we approach x maybe from the right side, and we've seen what happens to our curve on the right. Well, there's kind of two more places we can let x go. And that is, we can see what happens as we use larger and larger values for x. So we can see what happens if we use large positive numbers for x. And in this case, we're going to watch what happens, and we're going to see where our function goes as x gets larger and larger. So sometimes we call this the right end behavior of our function. And that's when we're letting x get large positive. Well, we could go in that direction. We can also go in the opposite direction. So we can let x get large negative. So that's going to be the other direction we can consider. And we'll call this the left end behavior. And so what we're going to do is we're going to watch what happens as we use larger and larger negative values. And we're going to see where does our function look like it's going. And this is a new type of limit. So what is the notation for this new type of limit? Well, to denote if we're going to let x get large positive, the way we're going to denote this is x is going to be approaching infinity. And there's kind of three options. Well, no, there's more than three options. But these are the bits of notation that we're going to see. So there's kind of the cases listed here, we can have a limit that approaches a specific number. And you want to think of this as the height of the curve. So this number L, you want to think of this as the height of the curve. So what we're seeing is that as x gets larger and larger positive, if we write that the limit of f of x as x goes to infinity is equal to some number L, what we're really saying is that the height of the curve is getting closer and closer to that specific height. And we'll see what this looks like graphically. Now, there are other options. The height of our curve could get bigger and bigger. So in that case, we write the limit of the function is infinite. And then we could also have the case where the height of our curve is getting large negative. And we write that the limit is equal to minus infinity. So you want to think of when we're doing these limits, x is going to be getting large positive or large negative. And there's a few different options for what can happen. The height of our curve can approach a specific height, a specific number. The height of our curve can just kind of go off the page and get really big. And the height of our curve can also go off the page, but in the other way, it can get really large negative. And just a little bit of notation here. So we're going to say the limit of f of x as x approaches infinity, we're going to use this again if x is getting large positive. And there's similar definitions here if we let x get large negative. And the only difference is we're going to write the limit of our function as x approaches minus infinity. So this is when x gets large negative. And we say x is approaching minus infinity. And then there's similar definitions. So there's technically 3 definitions for x approaching minus infinity. So there's 3 options. The height of our curve can approach a specific height in the kind of the left direction. The height of our curve can just get really big positive, or the height of our curve can get really big negative. So let's just kind of see an example, numerical example of actually, before we do this one, let's just back up. Let's go to this graph we were just looking at. And let's think about what is the limit going to be for this right end. So for this right end, we're going to calculate the limit, and our function name is g of x here. So we're going to calculate the right end, so x going to infinity, and then we'll also calculate the left end behavior. So if we're looking at the right end, x going to infinity, that we're over here now. And we're watching what happens. As x gets bigger and bigger, we want to see what does the height of our curve look like it's doing. And it looks like it just keeps going up and up and up and up. So we say that this limit is infinite. And if we go in the other direction, if we look at the left end, as x gets larger or negative, if we kind of follow the trend here, it looks like this graph is just going to get lower and lower and lower. So it's going to minus infinity. All right, so let's try some numerical examples. So here we have a graph of, or a table of some different function values. And on this, we have our x values in the first column. So we're using values of x here that are getting larger and larger positive. So what we can see as we read down this list here, these values are getting bigger and bigger. So we say x is going to infinity. And we have 3 different functions then, and the values for each of those functions at those specific x values. So we have this function f of x, and when we plug 100 into that function, we get 1.995. And if we kind of follow the trend here, if we're looking at what happens, when we plug in 1,000, we end up with 1.9997, and so on. And if we kind of see where these numbers are taking us, it looks like these function values are approaching the number 2. They're getting closer to the number 2. If we look at the function g of x, if we, again, kind of see what does it look like these numbers are doing, well, as the x values get larger and larger positive, it looks like the corresponding function values are also getting larger and larger positive. So we would say g of x is going to infinity. And then if we look at the third function, h of x, if we kind of see, well, what does the corresponding function values look like in this case, it looks like they're getting larger and larger negative. So we would say h of x is approaching minus infinity. So the notation for this is we would write the limit of f of x as x approaches infinity is equal to 2, because it looks like those function values are approaching 2. We would say the limit of g of x as x approaches infinity is equal to infinity, because it looks like those values were getting bigger and bigger positive. And we would say the limit of h of x as x approaches infinity is equal to minus infinity, because those function values look like they were getting bigger and bigger negative. And so this case, when a function approaches a specific number, something special happens to our graph. And that's called a horizontal asymptote. So a horizontal asymptote is a horizontal line, y equal to L. And this can happen if either the limit of our function, if we look at the left end, is equal to L, or the limit of our function as x approaches infinity is equal to L. So it can happen in either the left direction or the right direction, or both. It can happen in both directions. So let's just see a couple examples graphically of what this looks like. So here we have the graph of some function f of x, and we have this horizontal line y equals 1. And if we're looking at this right end behavior, what we're seeing is that the limit of this function as x approaches infinity, well, it's kind of bouncing back and forth, but it's decaying as we move further and further to the right. So it's still bouncing back and forth, but the amplitude is decaying over time here. And so as we move further and further to the right, it's still going to be bouncing back and forth, but it's getting closer and closer to that horizontal line. So we would say the limit of f of x as x approaches infinity is equal to 1. And that means this line is a horizontal asymptote. So horizontal asymptotes, what happens is our function gets closer and closer to that line as we move either further to the right or further to the left. So in this graph, we've only really pictured the right end behavior here. So, we know that this graph only has, conceivably, based on what we've shown, only has this one horizontal asymptote. Now, there's another graph here, and this is actually the inverse tan function. This graph has two horizontal asymptotes. So if we look in the right direction, what we can see is that if we watch what happens to our curve, it looks like as x gets larger and larger, the graph of the function is getting closer and closer to this line y equals 2.5. Actually, this isn't the arctan function. It looks similar, but it's not the arctan function. We'll see the arctan function in a little bit. So we would say in this case that the line y equals 2.5 is a horizontal asymptote. And a lot of times we'll abbreviate this HA. And what we're seeing, what happened there? So what we're seeing in this case is that the limit of our function f of x in this case, as x gets large positive, it looks like the height of our function is getting closer to 2.5. Now if we go in the left end, if we look in the other direction, it looks like as x gets large negative, now we're watching this way, what it looks like is our height of our curve is getting closer and closer to that value of -1. So it looks like the curve itself is getting closer and closer to this line y equals -1. And so that is also a horizontal asymptote. So we have, this graph has two horizontal asymptotes. And that's because if we look in the left direction, it looks like the height of our curve is getting close to -1. All right, so little practice here, graphic and with graphs and numerical tables, but we're going to want more of an algebraic approach, just like we've done before with other limits. And we're going to start by looking at power functions. So the first case, power functions x raised to the power n. So, and n here is, we're going to take this to be a positive integer. So 1, 2, 3, etc. So there's kind of different behaviors based on whether that exponent is even or odd power. Now, if it's an even, if we're looking at the right end where x is approaching infinity, the graph of our function has the same behavior. Doesn't matter whether it's an even or an odd power. So if we look at the right end, the graph is going up and up and up if it's an even power. And if it's odd power, also the graph is going up and up and up. if we look at the left end, excuse me, the graph is going up and up and up if it's an even power, but it's getting lower and lower if it's an odd power. So it just depends. X to the power n gets really large positive if n is even, and x to the power n is equal to, the limit is equal to minus infinity if n is odd. So it's going to be helpful to know these x to the power n's. And we'll talk more about these in class as well, all these different basic limits at infinity. But the other important one is 1 over x to the power n. Now this one's nice, and this is going to be our kind of the main one we rely on for a lot of our calculations, and that's because the limit of 1 over x to the power n is equal to 0 whether x goes to infinity or x goes to minus infinity. So you can see, and it doesn't matter the power, whether it's an even power or an odd power, the limit is still going to be 0. So if we look at, say, the even power here, as x approaches infinity, the height of our curve, it's getting closer to the x-axis. So the height is going to 0. And if we go in the other direction, if we watch what happens as x gets large negative, still the height of our curve is going to 0. So we say the limit is equal to 0. And actually, this means that we have a horizontal asymptote at y equals 0. So the x-axis is a horizontal asymptote in both of these cases. So let's see how we're going to use this. So we're going to jump ahead a little bit, and we're going to look at an example where we use that 1 over x to the power n, and we're going to calculate this limit at infinity using that algebra. So our function here is 3x squared minus x minus 2 divided by 5x squared plus 4x plus 1, and we're interested in what happens as x goes to infinity. And how are we going to do this? Well, this is different, fundamentally different type of limit, because we can't just plug in infinity. Infinity is not a number, so we just can't evaluate this function. So that was kind of our main strategy. Before, when x was approaching a number, what was the first thing we did? We would just take that number x is approaching, plug it into the function, and see what we get. And that would kind of dictate what happens. We can't do that here. Infinity is not a number. So we can't plug it in. Well, our strategy, we're going to call this the x to the power n method. And what we're going to do is we're going to identify the largest power of x in the denominator, and then we're going to multiply both the numerator and the denominator by 1 over that. So essentially, we're going to divide everything by x to the power n. All right, so let's see what we're going to do. Let's first pick out the biggest power of x in our denominator here. So the biggest one I see is this x squared. So let's just identify that. And our next step, and we can do this kind of a few ways, what we're going to do is we're going to multiply by 1 over that, 1 over x squared. And if we're going to multiply, we got to do it to both. We got to multiply both into the numerator, and then we also have to multiply that into the denominator, because all we're doing here is we're multiplying by a fancy 1. Now, technically, we are kind of changing the function because this is undefined at 0, but we're looking at limits where x is approaching infinity. So we're kind of getting away from 0. So this doesn't run into an issue here. And so if we distribute this, what we end up with, we're going to take this 1 over x squared, and we're going to distribute it to each term in our numerator. So what that looks like is we're going to end up with 3 over x squared divided by x squared minus x divided by x squared minus 2 divided by x squared. So all I've done is I've taken this and distributed it to each term. And then we do the same thing in the denominator. So we're going to take that same fraction and distribute it to each of those. So we're going to get 5x squared over x squared plus 4x over x squared plus 1 over x squared. All right, so there's our, looks like we've made this way more complicated. Well, now we're going to simplify it down. So we want to simplify each of these fractions as much as we can. And so in the first case, this first one, the x squareds just cancel out. We're left with just a 3. And then in the second case, one of the x's gets canceled out of the denominator, so we're just going to have a 1 over x. And then there's really nothing to simplify here. So we're going to have minus 2 over x squared. Okay, well, what about the denominator? Same thing. Let's simplify each of these fractions down. So the first one, the x squareds are going to cancel, so we're going to be left with just a 5. Then in the second one, this x is going to cancel out one of the x's there, so we'll have 4 over x. And then the 1 over x squared, nothing really to do there. And now, this is where we can use some of those previous basic limits. We're going to look at each of these individual fractions here. And if we kind of, let's just pop back up, slide up through our, we know from these special limits, 1 over a power of x is going to go to 0. So all those little fractions we have where we have a constant on the top and an x term in the denominator, they're all going to go to 0 as x gets large positive. So that means this 1 over x, that's going to go to 0. This 2 over x squared, that's going to go to 0. The 4 over x, that's going to 0. And then the 1 over x squared, that's also going to 0. So each of these individual fractions is going to be approaching 0. So when we actually calculate our limit here, this fraction goes to 0. Now the 3 just stays a 3. A constant just stays constant, doesn't change. So it doesn't matter, as x is approaching infinity, the constant 3 isn't going to change at all. It's just going to stay 3. So we end up with 3 minus 0 in the numerator. And then in the denominator, 5 plus 0 plus 0. And if we simplify this down, we end up with 3 over 5. And that's the value of our limit. And so this is, we've finally reached our destination. We've reached the logical conclusion of where does it look like our function is going as x is approaching infinity. So again, when we do this, we want to make sure we're using correct limit notation. So in all of our algebraic steps, we want to include the limit sign. But then once we reach our destination, no more limit sign. So no more limit sign there. All right, so this is going to be our common strategy for calculating these limits as x goes to infinity. And the reason is because infinity is not a number that we can plug in, so we have to kind of convert this into these expressions that actually do approach a number, a specific number, in this case 0, and then we can figure it out. All right, so we're going to look at a few more of these in class. So we'll see you then. Bye-bye.